Hello, it's Keith here, and this is the third in my series of Commander X16 tutorials in which we start looking at the early prototypes via emulator of the X16, and this time we're going to look at hardware sprites. We're going to learn how to use the hardware sprites and how to get some sprites on the screen, and we're going to see them animating as well. Now, first of all, I do have to make a bit of an apology. I wrote this tutorial a week or so ago, and unfortunately the emulator's actually changed since then, and they've renumbered some of the sprite addresses. So these have now changed quite considerably. Now the source code we're going to be looking at today has been corrected, but I haven't had time to correct the documentation. So if you're using the latest emulator, the example code we run through today and the addresses in that code will work fine. However, the addresses in this documentation are the old pre-version 31 addresses. The reason I've not changed them yet is I don't know, it's not going to change again tomorrow. So what I'm planning to do is once the X16 is basically released and the hardware is essentially fixed, I will probably recreate these tutorials again with the final hardware, with all the documentation updated and perfect. But at the moment, unfortunately, I can't keep chasing a moving target like that. So we're going to have to bear with things a little bit while the hardware's settling down. I will endeavour to keep my tutorial source codes up to date and working, and I will put comments in these videos where things have changed. But as I say, we're working with prototype hardware that is still under development, and I'm afraid this is just the nature of that. So please bear with me there. Okay, so let's start off by actually just seeing the example running then. So this is what we're going to be using today. So we've got this hello world message, which is our bitmap layer from before, and now this is a hardware sprite, and you can see it moving across the screen slowly, and it's also animating at the same time, and then it's going to get somewhere to, there we go, and it's just looped back. Now it didn't go completely off the screen there. The reason is I'm only setting one byte of the X position. You'd need to set both bytes to get a nice scroll off the screen. So it's just a very simple example there, so please bear with me on that. Now, when it comes to the sprite data, you can export sprites in the correct format for the Commander X16. We're going to be working at 4 bits per pixel, 16 colours today. The system can also do 256 colours. Now, you can see here we've got this sprite here, and if I just scroll through, you can see all the different stages here. So these are the animation frames we're going to be using for this crosshair. And if we go to 6502 here, Commander X16, we've got options here for save 4-bit per pixel and save 8-bit per pixel here. Now, by default, we're going to save these as 16 by 16. It takes this setting here, but the Commander X16 can actually do bigger sprites. We're just going to look at the small 16 by 16 one today, because I believe the procedure is basically the same. You just change one setting. So that's where we're getting our sprites from. We've got this data. It's included, if I go down to the bottom here, we're importing our sprite data just here, and we're going to have a look at that in just a moment. Okay, so the first thing is we have had to change some of our settings. So the high, medium and low address are now in the opposite order. Makes a lot of sense, as I say, I perfectly understand that. And they've also changed the addresses here. So the address that used to be 40040 is now F000, and various other ones have changed. This makes perfect sense. I think what they're doing is they are using the address space fully so that they can potentially have systems with much more memory later on. But as I say, I suspect you may see more things change, maybe adding extra bits or bytes to the tile bases and things to allow for larger memory allowances. So as I say, at this stage, we are chasing this moving target, so we've got something that will work today. If it stops working in the future, I will change the source code, but as I say, the documentation on my website, unfortunately, it's always going to be a little bit behind because it takes me potentially hours sometimes to write it. I can't keep changing it. So that's what we're going to be dealing with. Okay, so the starting is basically the same here. Now, the first thing we're doing here is we're turning our screen on. We're setting up our screen in the exact same way as before. We're defining our palette here. The palette address, all of these addresses have changed basically. We're setting up our bitmap layer here. We're setting this up, I think that's 4-bit per pixel mode 6 there. So we've got our screen set up here. And then we are now just clearing out our screen here, showing some hello world messages here. So this is all the same as in previous examples. Now this is the point where we're going to actually start working with the sprites. Now the first thing we need to do is we need to copy sprites into video memory somewhere. So The sprite data, the bitmap, is in our program code, so we need to transfer that to VRAM, and then once it's in the VRAM, we need to tell the sprite hardware, look in that VRAM for the sprite graphic that I want you to show. So that's kind of our procedure there. So first thing we need to do is we need to transfer to video memory, and I've decided to start using some more advanced commands to make the code a bit shorter and simpler. I've previously used calls to set up the VRAM addresses because I find that easier for people porting to other systems, but to be honest, it's becoming a little bit cumbersome, and so I've decided to start using a macro instead. So I've created this macro here called set VRAM address here, and what it will do is it will take a 24-bit value, it will split it up, and it will pass it to the H, M, and L, high, medium, and low bytes of the VRAM address in the exact same way as before. Now, before we were loading in A, Y, and X, and then calling set VRAM HML and things like that. This time we're going to be doing this command here, but of course the two are completely compatible. You could replace this with the original one. It's probably going to come down to depending on the assembly you're using, because this command may not work on the assembly you're using, just depending on how that assembler works with macros. Anyway, let's just discuss very simply what we're doing here. So we've got a sample 24-bit value here, and we're splitting it into three parts: the high part, the medium part, and the low part. The high part is the top two nibbles here. So what we're doing in VASM, the assembler I use to get that top nibble, is we're bit shifting it to the right 16 bits, effectively moving this part to this part. We're then ANDing in, this is a bitwise AND, with 255 here, which will essentially remove everything but these two parts here, because we need to make sure there's no junk here. And that will effectively strip out the 24 bits to just these two parts here. We store that in the high part. We then do the same again. We shift by 8 bits here. So we're taking this 3/4 part here and we're moving it to here. Now, when we do this, of course, the 1/2 part will be shifted to here. But because we're doing this AND here and doing the AND 255, everything above the bottom byte will be removed. So effectively, we're just left with this 3/4 part here in the low byte here. And we're loading that into 8, storing it into the mid part. The low part's even easier. We just AND in 255, that removes all of this part. And then we've effectively got those low two nibbles there. So that's how this command works within VASM. Now, depending on your assembler, you may be able to do this with bit shifts. Your assembler may not have bit shifts. It may work with divides. You might be able to use greater than or less thans to take a high and a low byte, but that didn't work with VASM with 24 bits. So this is what works with VASM. So you might need to come up with an equivalent. If you can't figure out an equivalent, if your assembler just won't do it, then what I'd suggest is you go back to this kind of idea, load in the high, medium, and low, and maybe just call a subroutine and get the subroutine to do it here, or something like that. As I say, you just need to get something that does the same thing. You don't have to use the same method here. But I figured, being as we've been covering the X16 a few times now, it was time to start making the code a bit simpler and just getting it as short as possible so we can discuss what's happening and not actually how it's happening as much. So that's what we're doing there. So this command here is selecting the address 10000 and it's setting an increment here. That's what that top nibble does. And then we are loading in 0 page entries marked as H and L. These are 0 page entries that I define by symbols. And we're loading the HL pair with the sprite address. We're loading the BC address with the sprite end minus the sprite start, which is effectively the length of the sprite. So we've got BC pointing to the length in 16-bit, HL pointing to the memory address in RAM, and we've got the VRAM address pointing to a destination, 10,000 here. So then we're calling a command called VLDIR. Well, what does VLDIR do? Well, if you're familiar with the old Z80, you can maybe guess. It's effectively copying BC bytes from HL into the VRAM graphics hardware, so into VRAM, effectively into the RAM address we just selected. So all we're doing here is we're loading from HL and we are basically incrementing our HL counter here. I could have actually taken this out, I think. Yes, a bit of an inefficiency there. I'm too used to 6502 code. We're of course using 65C02 here. So there's some commands that are available to me now that usually I'm not used to having. So anyway, so we're loading in from ZHL. We're storing to the VRAM hardware. We're then increasing HL here, decreasing BC, and we're repeating until BC reaches 0. So that's what we're doing there. So this command is just basically a simple way of saying, hey, dump all of this to video RAM at the address I told you before. So that's what we're doing there. we have got another function here called load pair. This is essentially the same as doing these here. We could replace this command here if I just run these out, and we specify ZHL, and then we specify the sprite address here. See, this works the same. So we have got this other command that I probably should have used here just to make things a bit clearer. So we can do that here, and we can do it here as well with BC. So again, this is another macro, and all it's doing is the equivalent of these commands just here. But as I say, it does. I'm not a massive fan of using these macros because it makes the code harder to read, but to be honest, with the way that the 6502 works with 16-bit numbers, it becomes an awful lot of code compared to the Z80 just to do something as simple as, you know, load a pair of 0-page entries with a word. So I do tend to use them, unfortunately. So anyway, so we're going to be using these load pairs a bit more now. And this is, at this point, we've now loaded our sprites into memory, and we want to actually start using those sprites. So how do we do that? Well, the first thing we need to do is turn the sprites on. This is now done by the hexadecimal address F4000. We have to write a 1 to that address, and that will turn the sprites on. Now what we need to do is we need to actually set up a sprite. And so what I've done is I've got a command called set sprite, and that's going to do all of the work of actually configuring the sprite within the video memory. Now, these are hardware sprites, of course. The way a hardware sprite works is you have these numbered hardware sprites, and each one has a set of attributes, and you would set those attributes, and then the sprite will draw onto the screen. And it doesn't matter what you then do to the screen. If you clear the screen, if you scroll the screen, the hardware sprite will always be in the same position, and it will always be perfectly drawn. So that hardware sprite, the hardware is dealing with the job of keeping that sprite visible. But the disadvantage of that is if you've got hardware sprite 0 and you set hardware sprite 0 to a smiley face, and then you want to draw a sad face next to it, well, if you set hardware sprite to the sad face, the smiley face will disappear because you've actually changed the hardware sprite. Whereas, of course, a software sprite, you could draw it twice in 2 different positions and it would appear twice. So when we're using the hardware sprite, we need to specify the number of the hardware sprite in the accumulator that we want to change. This code will then change that sprite, set the various attributes, the position, and the memory address of the bitmap data that's going to make up that sprite. So how does the hardware sprites actually work? Well, we've got the wrong memory addresses here because, as I say, they all changed after I did all of the documentation and all of the screenshots. You can see all of the addresses are now wrong in these screenshots here. But as I say, unfortunately, that's just the nature of things. So essentially, we've got the enable attribute here, which we've already set, and then each sprite has a total of 8 bytes. Now, these used to start from 40800, but they now don't. They now start from F500, I believe it is. And so we have the first byte is the address in video RAM that actually has the bitmap data for the sprite. So we just copied our sprite to video memory, or 4 sprites rather, for the 4 animation frames. So we would specify the address of the sprite part that we want to show. So we need to make sure our VRAM points to the correct one. Now we do have 2 modes. That's what the top nibble does, or the top bit even. If we set that bit to 1, we have a 256 color sprite. If we set it to 0, we have a 16 color sprite. My AccuSprite editor can export either one. We're looking at a 4-bit per pixel sprite at the moment, but as I say, you can do both. Now you then specify the X and Y position with a word each. Now, as you saw before, I was scrolling to the right-hand side of the screen, then disappearing. If I was setting all 9 bits, then it would have been much neater and it would have gone smoothly off the screen and could have come smoothly in on the other side. But as I say, I'm just being very crude to make the point. This is how it works. So we've got the X and Y position here, very straightforward. We've got some collision options. I'm not going to go into collision options. This is how you can detect if 2 objects have hit each other. I would tend to do that in software, to be honest, usually, just because I tend to find it easier, but as I say, it does apparently support that. The Z depth, that's how it affects the layering. We're going to want that to be at the very top. And then we've got flipping options, vertical and horizontal. Not going to make much difference on our crosshair, but we certainly have them. Very nice to have. Then we've got the height and the width. These can be 0, 1, 2 or 3, which will define 8, 16, 32 or 64 pixels. 64 pixels is huge, by the way, for hardware sprites. So we're going to be working with 16 pixels in today's example. It's a good size for your basic sprites. A palette offset, if you've got a 16 color sprite, well, you've got a 256 color palette. So as we've looked at in other things, you can set the offset of the palette so that you don't have to have everything on your screen using the same 16 colors. And then this is just for Sprite 0. There's, I believe, a total of 128 sprites. So these will then repeat from the following address ranges for the other sprites. So there we go. So there's the concept here. Now, you can see here that what we're doing here when we start is we've got the accumulator pointing to a hardware sprite number from 0 to 127. We've got IX and IY as in the 0 page as the X and Y position, 16 bits each. And then we've got ZHL pointing to a memory address. Now the memory bus is 20 bits of course, but we've only got 12 bits that we can specify the memory address in here. So what do we do? Well, what we have to do is we take the memory address that we've literally stored into video RAM, our sprite, and then we bit shift it 5 times to the right. Now if you want to work out how to do this, you can do this quite easily. So if we've saved to memory address 1000 for example, then if we do right 1, 2, 3, 4, 5, that's how we can effect a bit shift in our calculator here, and that will allow us to work out the addresses. You're going to know pretty quickly if you've done it wrong, though, of course, because your sprite's going to appear as a mess or not going to appear at all. But anyway, that's what we effectively have to do here to calculate the addresses of our sprites for passing to this function. So the first thing we need to do is work out the VRAM address of the sprite that we want to change the hardware sprite number. The sprite starts at hexadecimal F5000. Remember, you've got to be using version 31 or later for this example to work. I have saved the old versions in a subfolder in my sources download, but as I say, the version you're looking at here needs to be on version 31 or 32. We're running on 32 today because it's changed again, but there's been no technical changes that affect the code between 31 and 32. So we're multiplying A by 8 because there's 8 bytes per hardware sprite number, and then we are now storing that result, and then we're adding hexadecimal 50 here because the base is going to be 50 and then 00 here. So we're setting the top byte of the pair to adding 50 so that we've got that part there, and then we are setting the top byte to 1F here because we need to set the address to F5000, but we also want the auto increment. That's the auto increment nibble there. And then we set the address here using the old setVera HML, which will use the A, Y, and X registers in that order to set the memory address. So at this point, we're now pointing to our hardware sprite within our RAM here. And then we're just going to stream all of the values that we've got that we want to set that sprite up with. So the first one is the address here. So we're going to write those from H and L. So we load in ZL, write that. Load in ZH, write that. Remember, the top nibble of H will actually also do the color depth. We'll have a look at that in just a moment. Then we're loading in IXL and IXH. These are all 0-page entries. I've defined them as symbols, but you could do it in a different way. You could use pushed values on the stack or something, but that's how I tend to work. So we're using these IXL and IXH 0-page pair. The IY pair here, which is the Y position, of course. We're not using the collisions. We're not using the flipping. We are, however, setting the Z depth to the tops, so we're above all the other layers. I guess if you were using multiple layers of parallax, you could have your character running in between the bushes or something like they used to do in Mario. That's certainly an option here. And then here we are just setting the width to 1 and the height to 1. If we use 0, then we would be defining the sprite as 8 pixels. We're defining 16 by 16, that's why we're doing that. And we're setting the palette to 0, so we're using the base palette here. And that's really all we need to do to get one of the sprites working here. Now, if we just go back up here, so here is our function that actually defines the sprite. So we're defining our hardware sprite number here. We're setting it to 0, but we could equally set it to 1. That's just the way that's working. Now, what we could do, if we were going to be clever, is we could put an extra command in here. Now, before we were just using hardware sprite 0, but if we want, we can use multiple hardware sprites. So here we're defining hardware sprite 0. We're setting hardware sprite 0 to Y position 10. Then down here, we're setting the Y position to hexadecimal 51 here. And we're using hardware sprite 1 and setting a second sprite. So now if we run this, now we've actually got 2 sprites on the screen because they're 2 different hardware sprite numbers. But if I change this to number 0 here and run again, the top sprite has disappeared, and that's what I mean about hardware sprites, because we've actually moved the sprite with that second command. it won't work the same. And equally, if I take this code out and just put it here, now hardware sprite 1 is moving along and hardware sprite 0 is completely static. And as I said before, if we cleared the bitmap screen, the hello world would disappear, but this hardware sprite would still be in the same position, because that's what the hardware sprites do. The hardware is drawing that sprite all the time for us. So anyway, just a bit of fun there playing with the settings. I'll just undo all of that. So what we're doing here is we're loading the RAM address. We're setting it to 808, which is the memory address of one of the sprite tiles within the definition of the 4 frames that I've defined here. I think we could change this to 0 as well. That would work just fine. So I think 800 is the first frame and 808 is the second frame probably. We're setting our X and Y position and we're just setting the sprite here. Then what we're doing is we're loading in the address of the sprite data. We're increasing it here. We're just sort of doing a wrap here. And this is having the effect of moving to the next. I just realised there was a bug there. This should have been remmed out. This is for the 8-bit per pixel version, which we're going to look at in a moment. Anyway, so this code here is moving us to the next frame of animation for this sprite. And when we've got to the last frame of animation, which it's working out by just stripping some of the bits of the address out, it's looping around back to the first one. So you can see here we've got our scrolling animation here, and that's what that's doing. Now, when we've got down to here, we're just updating the L register here. We're then incrementing the X position, moving the sprite along the screen here, and we're just repeating around here. Now, let's have a go with that 256 color option. Now, if I just rem this out here, if you remember, the top nibble of the address, effectively the top bit, is enabling the 256 color mode. So if we set that to 8, that's setting that top bit there. If we run now, well, you can see our crosshairs got very, very small and the colors have gone weird, and that's because we're using 4-bit per pixel data and as an 8-bit per pixel sprite. Okay, well, we can fix that. All we need to do is go down to here. Where is it? Here we go. If we just disable that 4-bit per pixel version, enable the 8-bit per pixel version, both exported from Accu Sprite Editor here, just with the 6502 Command X16. We've got these two options here. So we can now enable that, and then all we need to do as well is well, actually, let's do it incorrectly first. We don't need to change the code that actually draws the sprite to the screen or loads it into memory, but what we do need to do is we need to change the code that's actually going to calculate the changing of the tile. We haven't done that, and that's now causing this weird flipping thing where it's kind of showing half a frame. The reason for that is that because we're now 8-bit per pixel, we're now using a 256 bytes per tile rather than 128. So what we need to do is actually change the code here. So if I just rem this version out here and unrem this version here and run again, there we go. That's working correctly again. Now, honestly, you can't tell because it's a 16 color drawing. I only drew this in, well, I think it's actually 8 colors technically, but it's not a 256 color image, so it doesn't make a lot of difference, but you can trust me, it is actually showing the 256 color sprite there. So there we go. That's given us a little simple function in this set sprite function that is going to allow us to actually quickly configure a hardware sprite. You can use this VLDIR command to quickly transfer data to VRAM. So maybe this will allow you to get started with hardware sprites. Now, we had a look at bitmap layers last time. We are going to look at tile layers. I'm already working on it. You can see just here. So we're going to be looking at how to create tile maps and how to use tile map graphics, which again, Accu Sprite Editor can export for you. So please stick around for that. I hope you're enjoying these tutorials. I apologize for the fact that there's a few little glitches in them with regards to addresses and things. Part of that's because I'm still inexperienced at it, and part of it is because, as I say, unfortunately the hardware is still changing. But as I've said before, I'll keep the source code as up to date as I possibly can, and once everything settles down, I plan to do these tutorials again in whatever the most appropriate way is, once we've got a clear understanding of what's going on with things. Anyway, I hope you've enjoyed this. Thanks for watching today, and goodbye. If you enjoyed today's lesson, please check out my website. We've got tutorials, source code and development tools for 6502, 68000 and Z80 systems, and a lot more systems coming in the future. We're going to be covering the 8086 and the ARM and a few other things as well going forwards. And if you've liked this lesson, if you've got questions, comments or suggestions on how it could be made better, please consider signing up to my forum. It's free, of course, and you can come along here and you can make suggestions, you can ask questions. And if you've got assembly projects you're working on, please let us know what they are. Maybe show off a few screenshots, tell us what things you've found interesting or what tricks you've come up with, because we'd love to know about it. Anyway, thanks for watching today, and goodbye.